We'll study something about Venturiemeter, how to determine rate of flow through Venturiemeter. Rate of flow is Q. Venturiemeter is installed in the pipe in order to determine Q of a particular pipe. Okay, so here we will derive the formula of Q, rate of flow through Venturiemeter. So how the formula is derived? The formula is derived by applying Bernoulli's equation. Bernoulli's equation is applied to the Venturiemeter. In the diagram you see we have indicated two points 1 and 2. This is inlet of the Venturiemeter, and the point number 2 is the throat. The throat is here, the diameter is reduced. This part is called throat of the Venturiemeter. And you also see the U2 manometer is connected, one end is connected to the inlet section and the other end is connected to the throat, and the difference of level of mercury is indicated by X. Okay, X is the difference of level of mercury in the two limb. So what we are doing here, we are applying Bernoulli's equation to 1 and 2. The statement of the Bernoulli's equation is that total energy at any point or at any section is constant. So what we have to do here, we have to see what is total energy at section 1. Total energy at section 1 is P1 by rho g plus V1 square by 2g plus Z1 is equal to total energy at section 2 at point 2, which is equal to P2 by rho g plus V2 square by 2g plus Z2. Okay. Now we are telling here that Z1 is equal to Z2. Z1 is the distance of 1 from the datum. Whatever datum you define, you have to define the datum. Okay, any datum you define here, the distance of Z1 from datum will be equal to distance of Z2 from datum. Z1 is distance of point 1 from datum, Z2 is distance of point 2 from datum. So in case of horizontal Venturiemeter, Z1 and Z2 will be same. In case of vertical Venturiemeter, in case of inclined Venturiemeter, Z1 is not equal to Z2. So we have taken the example of a horizontal Venturiemeter. Z1 will be equal to Z2, so that it is cancelled. So now what we have done here, we have taken the P2 by rho g on the left hand side. So we have this equation P1 by rho g minus P2 by rho g equal to V2 square by 2g minus V1 square by 2g. Now you see this term we are indicating it by H. H is nothing but difference of pressure head. So when I ask you what is pressure head at 1, you will tell me P1 by rho g. And if I ask you what is pressure head at 2, you will tell me it is P2 by rho g. Okay, so P1 by rho g minus P2 by rho g will give you difference of pressure head. So H is indicated here, which is nothing but difference of pressure head. Now you are substituting H for this, H equal to V2 square by 2g minus V1 square by 2g, and you see here we are invoking continuity equation. By invoking continuity equation, you can write V1 velocity at 1 V1 in terms of V2. So what is continuity equation? Continuity equation state it is A1 V1 equal to A2 V2, means discharge at any section is same. Discharge at section 1 is A1 V1 equal to discharge at section 2 is A2 V2. So you can equate these two terms and you will get V1 in terms of V2. We are substituting the value of V1 in terms of V2. You can see here, okay, H equal to V2 square by 2g minus this is V1 in terms of V2 divided by 2g. Okay, so now you can simplify this. Here we have taken V2 square by 2g as common. So this will be 1 minus A2 square divided by A1 square. Okay, so again you can simplify the equation. V2 square equal to 2gh into A1 square divided by A1 square minus A2 square. V2 equal to under root 2gh into a1 divided by under root a1 square minus a2 square. So we got the expression of V2. From V2 we have to determine the rate of flow Q or Q theoretical. Okay, so we know the formula of Q, which is equal to A1 V1 equal to A2 V2. Since we got the expression for V2, we can use this term A2 V2. So you see here Q equal to A2 V2. Just substitute the expression of V2 here. You will get this equation, and this is the formula of Q theoretical of Venturiemeter. So this is the derivation. So here we will see what is A1. A1 is area at the inlet. Okay, A1 is area at the inlet. A2 is area of the throat. So diameter of the inlet and the diameter of the throat will be given to you. From the diameter you can find A1 and A2. So you can find this. We need to see how to determine H. This H, which is nothing but difference of pressure head between the point 1 and 2. Here we will see how we can determine H for different condition. You see here, this is the formula of Q theoretical for a Venturiemeter. So A1 and A2 are easy to determine if the diameters are given. We have to see how we can determine H. There are different conditions. If we are dealing with horizontal Venturiemeter, okay, H is equal to P1 by rho g minus P2 by rho g. So this H equal to P1 by rho g minus P2 by rho g we have seen in the derivation. Okay, and in this condition, let's say that U-tube manometer is connected. Okay, so you see what U-tube manometer will give you. It will give you the reading. It will give you the reading of X. X is nothing but difference of level of manometric liquid or heavy liquid in the two limbs. Okay, so when U-tube manometer is connected, H is equal to X bracket SH by SO minus 1. Okay, so X is difference of level of mercury in the two limbs. SH is specific gravity of heavy liquid. Most oftenly it is mercury. SO is the specific gravity of liquid flowing in the pipe, minus 1. Okay, when we are dealing with the inclined Venturiemeter or vertical Venturiemeter. Okay, so when you are dealing with inclined Venturiemeter or vertical Venturiemeter, here also let's say that U-tube manometer is connected. Let's say I told you in the derivation that in case of inclined Venturiemeter, vertical Venturiemeter, Z1 is not equal to Z2. Okay, in case of horizontal Venturiemeter, Z1 is equal to Z2. So it was cancelled in the process of derivation, but here it will come. H is equal to P1 by rho g plus Z1 minus P2 by rho g plus Z2. Okay, equal to. So the relation between H and X will be same as indicated here. X SH by SO minus 1. Okay, in the third condition, I will note the third condition here only. In the third condition, inverted U-tube manometer is connected, not U-tube manometer, inverted U-tube manometer. Inverted U-tube manometer. So this is horizontal Venturiemeter connected with inverted U-tube manometer. So in case of inverted U-tube manometer, the manometric liquid is lighter, it is not heavier. In case of U-tube, the manometric liquid is heavier, mercury. So this H will not be equal to this. H will be equal to X bracket 1 minus SL by SO. X is difference of manometric liquid in the inverted U-tube. I will tell you it is like this. Okay, inverted U-tube manometer. Okay, so you can indicate manometric liquid like this. This will be X distance. X is nothing but difference of level of manometric liquid in the inverted U-tube manometer. So this is the formula, H equal to X 1 minus SL by SO. In case of inverted U-tube manometer, the manometric liquid is lighter. In case of U-tube it is heavier. We have taken the example of mercury here, but here it will be lighter liquid, and it is denoted, the specific gravity of the lighter liquid is denoted by SL. Okay, SO is the specific gravity of the liquid flowing in the pipe. Here also the fourth condition I will note here. Fourth condition, it's an inclined Venturiemeter, vertical Venturiemeter, but with inverted U-tube manometer. Inverted U-tube manometer. So H will not be equal to this term. It will be equal to X 1 minus SL by SO. Okay, so we have seen the four condition by which the H can be determined. When you have determined the H, the rate of flow can be determined. Here we will try to understand the difference between H and X. So this H is the difference of pressure head between the 2 points A and B, and X is the difference of level of manometric liquid in the U-tube manometer. So we will see how this relation is established. For that I have taken this arrangement. This is a differential U-tube manometer. Okay, both end is connected to point, this end is connected to point A in the pipe, and this end is connected to point B in the pipe. Okay, so I will take the lower level of mercury. Here the manometric liquid is mercury. Okay, and the liquid flowing in the pipe, let's say the liquid flowing in the pipe is water. So the density of water is rho W, and the density of heavy liquid mercury is rho Hg. Okay, so here I will take lower level of mercury low level of mercury as a datum. Okay, so what we know from the basic, pressure at this point is equal to pressure at this point. So pressure at this point is, you have to come from A to this level, PA plus this height is H1 and this is H2, plus pressure due to this liquid in the manometer, the height of this liquid is H1, rho W G H1 equal to, okay, so total pressure at this point is equal to total pressure at this point. So total pressure at this point is PB plus pressure due to this liquid rho W, here also water is there, rho W G H2. Then you have heavy liquid. then you have mercury. The length or the depth of the mercury here is x plus rho Hg, because the density of the mercury is rho Hg, g x. Pa, you can take Pb on left hand side. Pb equal to rho W GH2 plus rho Hg Gx minus rho W GH1. On the right hand side of the equation you have different densities, okay, rho W, rho Hg and rho W. So the density in the on the right hand side of the equation should be common, and this density, this mass density, should be written in terms of specific gravity. Okay, so here you see specific gravity of water equal to density of the liquid divided by density of standard liquid. So density of the standard liquid is water. Rho W equal to SW into rho W. Here you have mercury, so specific gravity of mercury equal to density of mercury divided by density of standard fluid, that is water in our case. Rho Hg equal to SHg into rho W. So this rho W, rho Hg and rho W should be written in terms of specific gravity. So Pa minus Pb equal to rho W is SW into rho W. Okay, you can also write it as SO because water is flowing in the pipe. SO is the specific gravity of a liquid flowing in the pipe. Okay, plus rho Hg in terms of specific gravity SHg into rho W into Gx minus again this rho W in terms of specific gravity SW into rho W. Okay, so instead of SW I will write SO. Okay, Pa minus Pb equal to SO into rho O plus and SHg can be written as SH, specific gravity of heavy liquid, rho O Gx minus SO into rho O. Here we have done mistake. We have not taken H2, GH2, and here we have not taken this GH1. Okay, GH1, GH2. So on the right hand side of the equation, rho G is common. Rho OG is common. Okay, so you see what you get here, SO into H2 plus SH X minus SOH1. Okay, so Pa minus Pb divided by rho OG equal to SHX plus, in this term SO is common, SOH2 minus H1. Okay, so Pa minus Pb is nothing but differential pressure head, which is denoted by H. Already we have seen in the derivation. H equal to SHX plus SO. H2 minus H1, you see in the figure, H1 minus H2 is X. Okay, so H2 minus H1 will be minus x okay. So h equal to shx minus sox. X you can take common here, x sh minus so, you can divide it by s naught, x sh by so minus 1. So we have derived the relation between this h and x, and we are most oftenly we are using in case of Venturiemeter, in case of orifice meter. So this h is head in terms of fluid flowing in pipe. Okay, it's like meter, if water is flowing in the pipe, meter of water. Okay, meter of oil, if oil is flowing in the pipe. So it is the head of water flowing in the pipe, and this x is nothing but head of heavy liquid.